Hey guys, I just want to go through the solutions to your practice questions very quickly. They're pretty straightforward, I think, so it shouldn't take too long. I'm betting this will be a 5-minute video, so good to have goals. All right, so first one we look at, these are all from Socos. You should probably recognize the format by now. We have a loop of an area of 8 centimeters squared and a magnetic field of magnitude 0.15 teslas. So what is the magnetic flux through the loop when the loop is perpendicular to the field, parallel to the field, and normal? The normal to the loop and the field will have an angle of 60 degrees between them. We'll look at that example here in a second. All right, first thing we should do immediately is convert centimeters squared to meters squared. And this is one way you might think about doing that. It's kind of the way I prefer to do it because it means I don't really have to think about it. You might just remember that 1 meter squared has 1,000 centimeters squared, but I don't necessarily like to remember things that I can easily derive quite quickly, and this is just one example of that. Okay, so there's my area. And if we look over here at part A, where our loop is perpendicular to the field, we measure our angle, remember, between the normal of the surface of the loop. So if you imagine my loop as a circle perpendicular to the field, then if I measure the angle of this purple line, if I measure the angle of the purple line to the magnetic field lines, what I'm going to find is I have an angle of 0. Okay, they're parallel. Okay, the loop is perpendicular. Its normal line, however, is parallel to the field. So what that means is that my angle theta is going to be 0. And then it's a very simple matter of just plugging it into the formula, which is, I'm quite confident, in your data booklet. Yes. Okay, so we plug it in, and that gives us our answer. We plug in all values, and that cosine of 0 degrees, of course, is going to be equal to 1. So easy peasy. All right, we look at part B, where the loop is parallel to the field. Okay, so if the loop is parallel with the field, that means that the normal line of the loop will be perpendicular to the field, and that is going to give us an angle of 90 degrees, which we then plug into the equation if we want to, but there's really no point. Because if the loop is parallel, it means there are no field lines passing through it, and we know that our magnetic field is going to be, our flux, magnetic flux, is going to be equal to 0. Okay, so where the surface of the loop is parallel to field lines, magnetic flux is 0. So you can imagine here another way to think about it, and this is pretty easy. In example A here, we have lines passing through the loop. In example B, there are no lines passing through the loop, so therefore no magnetic flux. Excuse me. For part C, sorry, my loop is now very badly drawn because I drew it by hand, but we can see here that the loop is tilted at an angle, and that just means that the magnitude of the magnetic flux is going to be less. One way to think about magnetic flux is in terms of vectors, and that's probably pretty apparent when you look actually at this. The math aficionados among you will recognize a cross product of two vectors, and that's exactly what we have here. Okay, so anyway, what we find then after plugging everything in is that we have 6.0 times 10 to the negative 5 Webers. And Webers, of course, are the unit of flux density. Okay, so next up, the magnetic field through a single loop of area 0.2 meters squared is changing at a rate of 4.0 teslas per second. What is the induced EMF? Okay, so just listing all the stuff I know here over on the left. My area is given. I'm also given this equation by the data booklet. We know that n is equal to 1 because we have one loop. Okay, so then I can further simplify my equation like so. We also know that flux density is equal to B times A times cosine of theta. We're given the change here in flux density. We're not given the angle, and it doesn't matter because we're given that change. So that's what matters in this particular example. Okay, we don't need our angle, so I don't need to worry about cosine of theta or sine of theta or any other thetas. The angle doesn't matter because we're given the rate of change. Okay, I can then rearrange my equation slightly because when we're talking about the change in the magnetic field strength over time, that is this guy, right? So it's just a matter of kind of identifying that. We then plug in the value 4.0 Teslas per second, and we multiply it by the area, and we're given negative 0.8 volts. Your book dropped the negative sign. I don't think it matters too much one way or the other. I kept the negative sign, but yeah, I mean, more often than not, we're interested in the magnitudes involved here. If we wanted to be really picky, though, I think my answer is probably better than the book. Probably. Okay, 11.3, very straightforward. We have a pair of conducting rails placed in a uniform magnetic field, and these rails are a distance apart, and we put a rod on the rail and push it to the right at a constant speed. This, as you can see, we are cutting field lines here, and that is going to induce an EMF and a loop. Okay, the loop, by the way, is of course going to be in this area. And as you move the conductor in this direction, of course, the size of the loop is going to increase. And again, because we're cutting field lines here, that means we're definitely going to have a change in magnetic flux. Okay, so that cutting of field lines, as you've probably seen from your reading, is one of the ways that we kind of describe change in magnetic flux density. Okay, from the data booklet, you will find this value, this formula. EMF is equal to the magnetic field strength times velocity times the length of a conductor. How convenient, that's exactly what we have here, except for 0.4 Teslas, which is left out of the original problem, but it's given to you here, so it's fine. Okay, so that will give us 4.8 times 10 to the negative 2 volts after we plug everything in, and it's fairly straightforward. Note that a little trickier question here that could easily be asked is, what is the direction of current through this conductor? And in order to figure that out, you would have to use a right-hand rule. And I'm not going to figure it out for you right this second. But it would be a good idea to think about because that is a very obvious implication of what's happening here. Okay, that's it, guys. I am done with this video. I don't know if I'm under 5 minutes, but I tried. Have a great day. Stay safe, and I will talk to you soon.